Recording in progress.
Hi. Today we're going to talk about Malthusian growth in age-structured populations. This is the outline of the class today. First, we're going to discuss how age and/or size might affect mortality and/or fecundity. Then we're going to derive age, size, structure, discrete time demographic models. Specifically, we're going to have a look at, Leslie, age-structured models, length of each stage structured models. We're going to talk briefly about the continuous size, discrete time integral projection models, the last generations of the discrete time models. And I want to mention there are, of course, continuous size, continuous time, partial differential equation models. We're not going to look at those in this class. I'm going to present general properties of the age, size, structure, and models, like the stable age or size distribution. I will introduce you to the Euler-Rota equations for Leslie models and talk about concepts like sensitivity and elasticity analysis. And last but not least, part of this class will be also the definition of basic demographic parameters and the introduction to life tables. Let's look at the first point, Malthusian growth in age or size structure model. The point here is that mortality is often a function of the age or the size of the developmental stage of the individuals. So mortality is not constant as we assume in the homogeneous Malthusian growth approach. For several marine animals, and for most of the animals in general, it might take several years before reaching sexual maturity. And once reproductive, the reproductive output can still be a function of the age or size of the individuals. In fish, typically, larger individuals have a larger investment in reproductive output, and so they might produce many more eggs than smaller individuals. Therefore, it makes sense to explicitly account for the age, size, stage specific changes of the basic vital rates, even in the context of density independence dynamics. Let's look at this. It's a very simple example. The population dynamics of the bay anchovy. We've seen this and we treat the dynamics in the case of homogeneous Malthusian growth. But we're going to introduce a little bit more realism now in this very simple dynamical model. In reality, bay anchovies may live up to 4 years at most. Reproduction occurs in the late spring, beginning of the summer, and the fecundity, the number of eggs per female over the entire reproductive season, is actually strongly age dependent. So females of 1 year old would produce on average about 5,000 eggs, of 2 years old about 10,000, of 3 years old, those that makes up to 3 years old, 50,000, and those who makes up to 4 years old up to 100,000. This is a rounded average expectation. We also assume the sex ratio is roughly 1-to-1. So on Edgewood, about 50% are females and 50% are assumed to be male. We then assume that egg survival to the 1 year old anchovy is assumed to be equal to 1/10,000. As for the other age classes, survival is as follows. There is a 30% of individuals of age 1 that will survive in the next year at age 2. 60% of individuals of age 2 that survive to the next year, when they will be age 3. And 40% of the individual will survive from age 3 to age 4. No anchovy are assumed to survive to age 5 or older. So this is the exercise we're going to start to do here in this class, and we'll continue to do actually in our lab. We assume to count population abundance every year just before reproduction. First things we need to do is to draw the graph describing the population life cycle. We then write the equation describing the dynamic of this population, and we will use R And as a matter of fact, you can use also Excel or MATLAB to simulate the population dynamics in the first 20 years or so, and trying with different assumptions about initial conditions. We will plot the number of individuals in each age class, as well as the total number of individuals as a function of time. I will ask you also to plot the same graph in a semi-logarithmic scale. I'll ask you, what do you see, guys? Lastly, we compute numerically the long-term finite, that is year-to-year growth rate, and the age distribution, that is the proportion of individuals in each age class. And we plot them against time again, and we will comment what we see. So if you want to challenge yourself, pause the video and try to do this exercise on your own. So let's look how we approach this problem. Well, we mentioned that we're going to count individuals just before reproduction, right? So that means that if we look at a newborn, when we count them at the end of the first year, they will be already 1 year old. That means we're going to count individuals of age 1, 2, 3, and 4. So we represent this as a graph of the life cycles in which we have a node for individuals of age 1, a node for individuals of age 2, of age 3, and of age 4. Then we need to account for the transition probability, that is for those individuals that will survive from age 1 to age 2 the following year. Those that survive from age 2 to age 3 and from age 3 to age 4. This is the arrow, what the arrow represent. And we call this sigma 1, sigma 2, and sigma 3, as we said in the previous slide. Now what is missing? Well, we need to take account of the newborn. And so we account for the per capita fecundity rate of individuals of age 1, the female of age 1, of age 2, age 3, and age 4. We will assume that the eggs will have the same probability of hatching and individuals to grow up to 1 year, and regardless the age of the mother and the age of the female. And so we know actually that this is a very strong assumption, and older, larger female might not only produce more eggs, but also more viable eggs, larger eggs that can survive better. We won't make this assumption here for the sake of simplicity, but you will often find this in more realistic models or information about species. So we now have the full life cycle that is described here in this graph. And let's say that M of xt is the number of individuals in age class X at time t. What we need to do now is to write equations that tell me how many individuals of age 1 or 2 or 3 or 4 will be alive next year. Well, this is very easy for class 2, 3, and 4, because the number of individuals of age 4 that will be alive next year is equal to the number of individuals of age 3 that are alive this year, multiplied by the transition probability from age 3 to age 4, that is by sigma 3. Likewise, the number of individuals of age 3 that will be alive next year is equal to the number of individuals that are alive these years of age 2 that will make it to age 3. So n2 times t multiplied by sigma 2. And likewise, n2 times t plus 1 is equal to sigma 1 times n1 times t. Now we have to write the first equation. And in the first equation, we have to account for how many individuals we have in each reproductive class, which is all the classes we have here. How many of them are female? Remember about the sex ratio. And so we account for their per capita fecundity, which is age dependent. And finally, for sigma 0. that is the survival from X to individuals of 1 year of age the following year. And we do this way. In here, I have collected already 1/2 to account for sex ratio, which apply to all the classes. And likewise for sigma 0, which is assumed to be independent upon age. And then I have accounted here for the number of individuals of H1 times their per capita fecundity, number of individuals H2 times per capita fecundity. Remember, we always have 1/2 to account for the female, and F3 and 4 F4. This equation is also known as renewal equation. Now, this is a very convenient way of writing this model and implementing that in RScript or in MATLAB or any other computer language, of course. There is a much more synthetic way to represent all these models and the different equation, which is the one that I reported here. Here we have defined a vector, capital N is an variable times t, which is the number of individuals of age 1, 2, 3, 4 times t, and a transition matrix, which is known as the Leslie matrix. This matrix has some specific property. The classic Leslie matrix has the elements on the main diagonal, which are all equal 0 except for the first class, if the age 1 individuals are reproductive. Oops. Sorry about that. And in addition, the elements of the subdiagonals are sigma 1, sigma 2, and sigma 3, which represent the survivals of individuals of age 1 until age 2, and sigma 2, the survival of individuals of age 2 to up to sigma 3, and up to age 3, and sigma 3 is the survival of individuals of age 3 up to age 4. The element of the renewal equations are here. And then I can represent the old model that we saw before, sometimes with a lot of equation, in a super synthetic form. I have the vector of number of individuals at different ages times t that provide a vector multiplication with the matrix, the transition matrix, the Leslie matrix, to provide the number of individuals in each age class at times t plus 1. And I'm sure you appreciate that this is a really synthetic form. In this case, we only have 4 age classes, but for a lot of marine mammals, for instance, the life expectancy might be much longer, 20 years or many more. And so writing down every single equation one by one might just take a lot of space and might not even be super clear. And so the matrix formulation of the Leslie model is actually a really elegant way to represent the dynamics and even to implement this into an RScript. So we'll do that together in class, but let me show you the outcome. We can basically take the model parameters, substitute into the transition matrix here. So we have values for sigma 0 estimates, for sigma 0, sigma 1, sigma 2, sigma 3, and for fecundity as a function of age. And we can substitute that and run simulation, as I'm going to show you now, the output, which is represented here. First, we're going to plot the number of individuals in each age class as a function of time, and the total number of individuals as a function of time as well. The total number of individuals is given by the sum of the individuals in each age class at time t. Well, when I plot it here, I see that, let's see what I see then. Well, first of all, so the black thick line here is the total number of individuals, while this is the number of individuals in age 1, age 2, age 3, and age 4. We got generational time on the horizontal axis and the number of individuals on the vertical axis. And what I see here is that depending upon what we call mathematically the initial condition, what is the initial population structure, the population fluctuates in the first years quite a lot, but at some point it reached a fairly smooth growth, which is again a geometric growth. Okay, so we know that the property of a geometric growth is that when we plot this in a logarithmic forms, at least in the homogeneous Malthusian case, it produces a straight line. Let's see whether this is the case, and indeed this is the case as well. So there are quite wide fluctuations potentially in the beginning, depending upon the initial conditions, but then the population, you see, increases definitely in a geometric form. And then let's have a look here. I plotted the finite growth rate at time t, so the ratio between the total number of individuals at time t plus 1 divided by the total number of individuals at time t. And I see that, yes, there are fluctuations that depends again from upon the initial condition, but eventually this level off. And in this specific case, well, you can barely see because there is a dotted line here, that's one. And the finite growth rate is just above it, but just enough to produce this population growth in the population here. And the last things I want to show you guys is to plot the proportion of individuals in each age class at each time step, which is reported here. This is called age distribution, is the ratio between the number of individuals in class X of age X times T divided by the total number of individuals the same year. And we'll call it with the Greek letter pi of age X and times T. And what I see here, so red is H1, and then we got H2, H3, and H4. What we see here clearly that this age distribution fluctuate quite dramatically depending upon the initial condition, but eventually reach stability. Okay? And this is called the stable age distributions. We're gonna run this exercise together in R during the lab. This model, the Leslie model, have a specific property is that in the long run, the population reaches a stable age distribution, pi of x. I want you to pay attention that there is no time index here. Subscript is just pi of x. This is the long-term age distribution of the population. And on a simple model like the anchovy one with 4 equations, we can show analytically to all the steps that this age distribution is at age x is proportional to this parameter pi of x times lambda to the power of minus x divided by a normalizing constant, because the sum of the pi of x over all the ages need to be equal to 1. And lambda is the long-term finite growth rate of the population, the one that we simulated numerically before. In the long term, is the finite growth rate of the population. And P of x is the so-called survivorship function. That is the probability that an individual at birth has to live until age x. And this probability, of course, at birth is equal to 1 by definition, and then it can be computed as follows. So in a recursive way, the probability of individuals at birth to live up to age 1 is equal to the probability of surviving until the previous year times the survival from the previous years to this year. So in this case would be P0 times sigma 0. The probability of surviving until age 2, from birth to age 2, is equal to the probability of surviving from birth to age 1 times the survival from age 1 to age 2. So it's P1 times sigma 1. So in general, we can write this as P of x plus 1 is equal to P of x. So the probability of surviving until age x plus 1 is equal to the probability of surviving from birth to age x times the fraction of individuals, the probability of surviving from age x to age x plus 1, which we have indicated as sigma x. And because P of x can be computed recursively, in general, we can say that P of x plus 1 is equal to sigma 0, sigma 1, sigma 2 to sigma x. So basically, this formula here is derived by using information of the age-specific animal survival for our anchovies and as well for the finite growth rate of the population. And we'll learn how to derive that. Okay. For this type of model, and only for the Leslie models, the finite growth rate can be computed numerically, either simulating the population or by solving the Euler-Lotta equation in discrete time. That is the sum on all the reproductive ages of the probability of survival until age X times the net fecundity, so the number of females generated by the mothers at age X, times lambda to the power of minus X. And this needs to be equal to 1. So if I have the survival from the annual survival, I can compute the survivorship function. I have the age-specific fecundities. And then this is the only unknown. This equation cannot be solved analytically, but numerically, it's usually a piece of cake and can be done. For population for which we make an assumption of continuous time reproduction, the Euler-Lotta equation, instead of having a sum for each discrete age and the age-specific fecundity, we have an integral, which is basically the equivalent of the sum when the integration, the interval between two ages become really small, of nu of x, which is the net fecundity, already accounting for the sex ratio, and p of x, that is survivorship until age x, which is not different from the previous one, times to e to the power of minus r times x. Because we know that e to the power minus r is actually the finite growth rate of the population. And of course, I put here from age, it goes from 0 to infinite, but in practice, you integrate this from the age at first reproduction, because the fecundity rate before is equal to 0, and until to the maximum age of the individuals in which they are reproductive. And given that, we now take a little break before we move to look at a stage structure population.